Hello and welcome to another video on data mining. Today we are going to talk about regression. Now we've already talked about classification, which is in which the goal is we want to use the existing feature representation of an object to classify the object into a certain type. Uh, However, that is not the only type of machine learning problem. It's one of those problems that is really easy to start off with in machine learning, but there are a bunch of other problems or other types of machine learning problems, such as regression, there is ranking, and we're going to talk about those now that we have a good understanding of the foundations of machine learning in terms of the REO principles as well as structural risk minimization. So unlike classification, in which we want to classify a given object into a certain type, for example, we want to predict the gender of a person based on their picture, that would be a classification problem. However, if you want to predict the age of a person, then that would be a regression problem. What we want to do is we want to use this figure as or this picture as input, and we want a numerical output, and that output has a relationship. So, for example, 27 is greater than uh, 20. So the age of a person of with age 27 has a relationship which is a greater than relationship in terms of the age of a person whose age is 20, right? So if there is such a relationship, such a numerical relationship of greater than or less than, then we can use regression. Whereas an apple, for example, is we cannot say that it is greater than an orange or anything like that, right? So there's no definition of this greater than sign or less than sign, or for example, when you're predicting gender, we cannot say that male is greater than female and so on, right? But in terms of age prediction, for example, we are trying to predict a real valued quantity, and that quantity, different objects possessing that quantity will have these different types of relationships. Okay, so what we want to do is predict a continuous variable as output typically, and instead of a discrete variable as in classification, where we can represent -1 as to belong to one class as to the negative class and +1 to belong to the other class. But more importantly, it's really important to understand that in classification, even though we may say that, let's say we can represent apples as -1 and oranges as +1, typically we cannot say that as an apple is greater than orange, whereas in regression, we are able to say, make such a statement that a person with age 27 has larger age than a person of age 20. Okay, so what we want to do in this case, for example, is give this image as an input. Instead of detecting or predicting a class for this image, we want to predict this real valued quantity, which is 27. So we have a data set of these images in which we know the age, the true age of the person, and we want to use that training data set to generate a regression model, so that if I give it an input image or the features of that image, we get a predicted age. We can compare that age to the true value, and that is what our loss function is going to be. Just like in classification, we want to say that if the predicted class matches the true class of a given object, then there is no error. Similarly, we're going to say that if the amount of error between the prediction and the actual is going to be the difference between the predicted value and the actual value in case of regression. So it's a bit easier in terms of the loss function in comparison to classification. We can plot the real value of the age of a person against their predicted value. And what we can see is that if the predicted value and the real value match up pretty nicely, like the ones that we see over here, for example, for a given person whose image was given to the machine learning model, the real value of the age of that person was around, let's say, 90 years, and what the machine learning model predicted was 80 years, and the amount of error we have between the two is 10 years, of course. But we can do that for a number of different examples, and we can see whether the correlation between these two, the predicted and the actual values or the real values, is good or not. Ideally, all of these points, the real values should be lie. So all of these points should lie on this line. So the real value should match up exactly with the predicted value. That would lead to an error of 0 and an ideal correlation coefficient between the two of 1.0. So I hope you have a good idea of what we are trying to do here. We're trying to predict real world quantities for a given image using machine learning. So the goal is, again, in statistics, typically, regression is defined as as an attempt to or as a way of estimating the relationship between variables. We can have dependent variables and we can have independent variables. Let's say we've got the same height versus weight problem, and you have got the height as on the x-axis in some units and the weight on the y-axis in some units. And what we want to do is to identify that relationship or quantize or estimate the relationship between height and weight. And one way of doing that is try to fit a line to this data set, and which you can see over here has been done. And if that line is a good fit between the two, we would say that the relationship between these two variables is linear, right? So in this case, we would be using h over here as the independent variable. That would be the input variable in this case. And w would be the dependent variable or the prediction variable. Okay, and in case of the age prediction example, we can have different features. Let's say we've got a feature that measures certain characteristics of the face of a person. Let's call it feature one. It doesn't matter. We don't need to define it, but we want to use that feature to predict age. Okay, so on the y-axis we plot age, and on the x-axis we plot this independent variable, which is feature one. And what we want to do is we want to identify the relationship between the two. And we can have multiple variables instead of having a single variable, and that is typically the case. We can derive a bunch of features from the given face image of a person, and we can correlate it or we can regress that to the age variable over the training data set. And that is going to give us a relationship between the two. Okay, and these regression schemes are typically used in prediction and forecasting. So let's say if you've got a given variable x, what we really want to do is to generate a prediction using a machine learning model, which is given by this function f over here, so that the output, the true output, the quantity for this particular example matches the predicted quantity. Okay, so that's what we really want to do. The objective is to estimate then the parameters W that produce outputs that are closest to the given targets. Let's say for a given data set, you have a data set like this. You've got these independent variables. You've got an example whose x value or independent variable value is 1, and the dependent variable value is 3.5. You've got another variable 2, example number 2, whose x value or the feature value is 2, and the corresponding y value is 4.75. And what you want to do is to find a mapping function, which is f over here in this case, that allows you to go from here to here on unseen test examples. So you can think of it like this. We use a training data set in which we have images with known ages of different people, and we want to use that data set to build a machine learning model that takes an input as an image and spits out the age of that person on the other side. Okay, and we want to minimize the error between the training and uh, the prediction output and the actual label over the training data. So we've already covered different preliminaries, but if you want to take a look at some of these relations because we're going to use them, please go pause this video and try to understand what's going on over here. How can we represent a sum of products in terms of dot products? And how can we represent a system of linear equations in terms of a matrix vector product? Okay, so please go ahead and do that. There is also a video on that, and I welcome you to try it out. Uh, Now, what we are going to do is we are going to try to do what is called ordinary least square linear regression. And this is something that you would have done, or cousin of it, you would have done earlier in your high school or in an earlier math class. Okay. So let's say if you got a bunch of values like this one. So let's say you've got two values. I'm going to call them feature one and feature two. And then we have output value that I'm going to call y, or let's call that target value t. So let's say you got an input 0, 0, and you got a corresponding target value, which is, let's say, -1, 0, 1, which is 1, 1, 0, which is 1, and 1, 1, which is 1, let's say. So let's say you've got a bunch of these values, okay, and you've got a corresponding target for them. So if you think of it, if you want to fit a linear function to it, then this can be modeled as a system in which, as a system of linear equations. There are four examples, and we are going to do that modeling. Okay, so let's say if you got a linear predictor, that means if you have, let's say, only two features, x1 and x2 over here, then for a given example, x, we can generate the prediction score f of x for this particular example by multiplying the first feature value with weight w1, this should be w2 over here, and we can add a bias term to it, okay? Or alternatively, we can express it in more generic terms in uh, good old dot products. So for a given example, we compute the score of that example or the prediction score of that example by projecting it onto this W vector, and we add a bias term to it. And if you are not interested in adding an additional bias term, what we can do is we can change the definition of our weight vector to include the bias term by simply adding a 1 as an additional feature in our x. And if you take the dot product of this and this, it's going to be exactly this thing. So that's not a big problem. So wherever you see W transpose X, you can easily consider W transpose X plus B. Let's say we've got a bunch of examples. For example, number one, our prediction score, for example, number one is going to be W transpose X1, and we can also write it as X1 transpose W. For a given example, X2, we can calculate its prediction score, and it's going to come out W transpose X2 or the X2 transpose Wn. And if we have a bunch of n examples, and then the nth example can also be the score of that can be expressed like this, or in general, we can write all of these linear equations in this form. So if you have a data matrix in which each row is an example, then we can calculate the decision function score for all of those examples by calculating this matrix vector product. Let's say if x is, let's say, n has n example, and each of those examples in d dimensions, then you have got a weight vector which is also in d dimensions. So if you multiply these two, then you're going to get a matrix of size n cross 1 at the output, which is your matrix F. So this is just a compact way of writing these systems of equations, okay? So nothing more than that. So if you have the single data matrix can be represented like this. This is the first example. So we have got the first feature, the first example and all of its features, D features. And this one we have that because we want to model the bias term. Similarly, we have the second example over here, and then we have got the nth example over here. So this is your overall data matrix. All we want to do now is try to find out this W so that once I multiply this X with that W, the prediction value, which is F in this case, should be as close as the corresponding target value that we have been given for each of those examples. Let's say the target value, the true ground truth value or the target value for the age of a person is, we call it the variable yi. So if this is the true label in the training data set for each of those n examples. So for the first example, the age is y1 is equal to, let's say, 20 years, and for y2, for the next person, it is 30 years or something. Then we have got that as in the variable yi. And the prediction output that we want to generate from our linear function is going to be f of xi comma w. And the difference between the two and the square of that distance is going to give us how much error we have over that particular prediction. So this is, if you break it down into the REO principle, what we are trying to do, we have a representation which is simply W transpose X. What we are doing right now is this evaluation bit, and we were trying to measure how much error would we have for a given example. So for a given example, if we know the true value of that or the target value of that regression output, in this case age, then that is yi, and then the difference between the two, or the square of the difference between the two, is going to give us how much error we have for this particular example. So we can express the error of each one of our given examples like this one. The error for the first example is going to be calculated using this thing. The error for the second example, just substitute the second example features and the target value for that. The weight remain the same. And then we can do it for all of these examples. And this is also a system of linear equations. And what that allows us to do is we can express this in matrix form like this. So the error of all of those examples can be written in this form. E is equal to xw minus y. Remember, xw was the prediction output. We just calculated it. We called it f. So the error we have is f minus y. And for us, positive errors are as bad as negative errors. So what we really want to do is to calculate the norm of this error vector or the sum of squares of these errors. And we can easily do that by taking the dot product of this E vector, which has n components now, one corresponding to each example. We can calculate the dot product of it with itself to compute the loss function or the evaluation function. Now, the larger this value of loss, the worse the classifier is, right? And what we want to do is we want to find this W so that this error term is minimized, right? That's the third part, that is the optimization bit of this problem, right? So that's what we will do next. So we want to find a W that minimizes this loss function, or we can express it that in more mathematical terms, that we want to find a minimizer of this loss function, or we can say that W star is going to be the value of W that minimizes this thing. And we can achieve that by taking the derivative of this loss function, which is the square of the sum of square errors uh, for a given example or for all of the examples in our data set, in our training data set. And we express that like this. So it is xw minus y, which was our definition of error, transpose multiplied by xw minus y. And if we expand that, this is the expression we get. Okay, and using our very simple laws of vector algebra, which are given over here, if we go ahead and calculate the derivative of this loss function with respect to w and substitute it equal to 0, then what we get is the following terms. So the first derivative that we do is using so w transpose x transpose xw. This is the rule that we apply. So if you want to take the derivative of that, that's going to come out to be 2 times x transpose xw. We have got these two terms here, and if we take the derivative of that, that's going to come out to be 2 times x transpose y. Since this is a constant, therefore the derivative of this with respect to w, it doesn't have any w terms in it, is going to be 0. And if we substitute it equal to 0, this is the expression we get, right? And then what we get is w, we can take the inverse of this whole thing on both sides, and that is called that. Then we get an expression for w. Remember, we were interested in finding w or a w star that minimizes this, that minimizes the overall error, and this is the expression that we get. We know what our data matrix looks like, right? We have all the features for all examples, and for each of our examples, we know the target value. So everything on the right-hand side of this equation is known, and that means we can go ahead and calculate the weight vector. This thing over here is called pseudo inverse. So if you studied systems of linear equations, then it's really easy to relate to that. We must have solved an optimization problem like the system of linear equations expressed like this, that x is equal to a inverse b, right? This is a generalization of that, right? And the reason we require a generalization is we can only calculate inverse of some of a matrix if it's a square matrix. But our data matrix is not a square matrix, it's a matrix of size n cross d, right? So if it were a square matrix, then we could use the same principle and we could extract our weight vector over here. But because our x value is not, the x matrix is not a square matrix, we would not be able to do that. So this is the expression we get, which is a minimizer of this optimization problem that is given over here. And if you think about it, if you've got a matrix of size n cross d, then the transpose of that, then let's calculate that dimensionality of the pseudo inverse, as I'm calling it, okay, of this thing. So if we calculate x transpose x, then that's going to be a matrix of size d cross n cross n cross d, or in other words, that's going to be a d by d matrix, and the inverse of that is going to be a matrix of size d by d as well, right? And then we've got an x transpose over here, and that is a matrix of size d cross n. And if you multiply a d by d matrix with an n by n, d by n matrix, you're going to get a d by n matrix. So this thing over here is a d by n matrix. And then we've got n by 1 vector over here that is being multiplied, and that's going to give us our d-dimensional weight vector that we can now use Okay, so I hope this method makes sense to you. What we have done so far is for each of our given examples, we were given a real valued output and we were given a bunch of features. And we wanted to find a weight vector W that minimizes the sum of square errors of for our given problem. We had a linear classifier that generated a prediction score for each of those examples. And what we wanted to do is to reduce the sum of square errors. We knew the target value for the training data set for a given example, and we subtracted the prediction output minus the target value, and we squared it, and we did it for all of our examples. And if we solve the resulting optimization problem, then we end up with an expression of W. And all it requires is calculating an inverse of a matrix and multiplying it with a vector. That's pretty much it. Okay, so if we go ahead and do that, this is a very simple example of that. Let's say if we got two examples only, the first example is 1, 1. And remember, the only reason we have a 1 over here is because we didn't want to add a bias term. Okay, so let's say if we got, this is our first example with the feature value of 1, and the second example has a feature value of 2, and the corresponding target value is for the first example is 3.5, and the corresponding target value for the second example is 4.75. Then if you use the expression that we've just derived, then the weight vector is going to come out to be this value. Okay, and now if we go ahead and multiply our given example, the first example, which is 1, 1, if we multiply it with this weight vector, which is 1.25, 2.25, then the value that we get at the output is 3.5, which matches our training data value. Similarly, if you got another example, we get 4.75 for this particular example, 2, comma 1, with the same vector. So what we've done essentially is we fit a line to these 2 points. So that's another way of fitting a line to these 2 points. Even if you have like three other points, you would still be able to find what is called a mean square error or a sum of square error minimizer or a sum of square error fit to this particular problem. Okay, so that is called ordinary least square regression. And the reason it is called ordinary because there is nothing special about it, right? And it's called least square because we are trying to reduce the sum of square errors. And that's what we do over here. If you want to code this up, it's really easy code. So you got a training data example. You got two examples in here. For the first example, the feature value, it's only a single feature, which is 1, and then you got another feature, which is 2. What we want to do is we want to append ones to each one of them because we don't want to model the bias term. And we can do that by using this expression. We know the target values for those, and this is the expression for calculating the pseudo inverse. It's also called P inverse, and that's going to give us this W vector, and then I can use this W vector to calculate the prediction output by simply multiplying the given data matrix we have with this weight vector, and we can go ahead and calculate how much error that produces or the sum of square errors over here. And that's what has been done over here. On the x-axis is the feature value, on the y-axis is the output. We know that the target output for this particular example, whose feature value was 1, is 3.5, whereas for the example whose x value was 2, the target value is 4.75. And if we use this particular piece of code, then we get that the prediction matches exactly with the target output. And that's also shown in this prediction plot on the right-hand side. We plot the true value, which is 3.5 for one example and 4.75 for another example. And then we plot the predicted value for these two examples like this. So that is 3.5 as well. And then this is 4.75 as well. So that is a very good fit, right? So that's what we've done over here. So this is a regression scatter plot, whereas this is a data plot. And I hope that you are now familiar with the concept of OLSR. And it's a really simple method. There is nothing too complicated about it. If you got a bunch of data and you have got a set of target values, you can use you can use OLSR to go from X to Y, okay? If the relationship between X and Y or the various features of X and Y is linear. sklearn already has a built-in linear regression tool, so you don't even need to do this much of coding in sklearn in Python. So if you import that, you have your data matrix X, And you can train a machine learning model or an ordinary least square regression by simply using this statement over here. You've got your x and your y, you pass it to your fit function as always, and out comes the regression value, right? And then you can generate predictions for a given x value using this particular function. So it's really easy. You can identify the different coefficients or the weight vectors using this particular value or this particular expression, as you can see on your screens. Now there's a small or a subtle point here. If you set fit intercept is equal to false, then what would happen is that it would try to generate a fit from x to y without adding a bias term to your feature values. However, if you set your fit intercept is equal to true, then it would add a bias term to your expression. Okay, so that's the only difference between the two, and you can use this code for solving other type of regression problems. Okay. Uh, Next, what we are going to do is we are going to discuss different problems in using ordinary least square regression. But I think you can conclude we will conclude this video here, so you can go ahead and play with these very simple codes for multiple points, like 3 or 5 points that you can generate, and see whether you're able to find a line that fits all of these points. Thank you.